Now, for those of you who are not familiar with the Quanti, we were founded in 2012 by some UW or University of Waterloo alumni and the principal developers of HydroGeoSphere. Today, the company has grown to more than 20 employees, and as you can see, we maintain a heavy focus on research and development. Almost all of our R&D and consulting work is centered around HydroGeoSphere, the world's most powerful integrated hydrologic modeling platform. HydroGeoSphere, or HGS, is a three-dimensional control volume finite element simulator, which is designed to model the entire terrestrial portion of the hydrologic cycle. In order to build these simulations, it is of course necessary to recreate the model domain using some sort of grid or mesh, and our recommended tool to generate these meshes is of course AlgoMesh, developed by our friends at HydroAlgorithmics. Now, to explain why exactly it is that we recommend AlgoMesh, I'm joined by my colleague Amanda Taylor today. Amanda is a geologic modeler and one of the Quanti's resident AlgoMesh users. Her past research experience has focused on regional 3D geologic modeling of quaternary sediments for seismic risk assessment in eastern Canada. Since joining a Quanti in 2018, she has worked on many projects and has helped to build and incorporate geologic models and other spatial data sets for HGS models at various scales. Amanda will kick us off today by delivering a presentation on the benefits of using unstructured finite element meshes for groundwater and surface water modeling, why we highly recommend AlgoMesh to construct these meshes, and the different algorithms that actually power AlgoMesh. She'll also review the basic workflow that one would use to actually build a mesh using AlgoMesh and highlight common data preparation techniques and potential issues that you might run into while building your meshes. And when the presentation is complete, I'll run through a quick tutorial to demonstrate what we've learned, at which point everyone will have a chance to work with AlgoMesh themselves. The training package and training materials, which I had sent or emailed to everyone on Monday, does include some installation instructions for AlgoMesh, so hopefully you have it installed and are ready to go today. Now, we don't expect that this training session will take the full amount of time that we've scheduled on your calendars, but Amanda and I will remain available for the full duration just in case you have any questions at the end of the session. So again, I'll invite everyone to list any questions that they have for Amanda or I in the chat menu here in Microsoft Teams. And with that, I'll pass things over to Amanda.
Great, thanks, Braden. So I'll probably get to any questions that you put in the chat once I get to the end of my presentation. So just know that your question won't be ignored. I'll get to it once this presentation is done. So to start off our conversation today, we're going to go back to the basics and discuss a bit about model discretization. HydroGeoSphere uses a control volume finite element method to solve the flow equations in the model domain. This means that we need to subdivide the model domain into distinct elements in order to solve the equations. This act of splitting up the model domain into elements is what we're referring to when we talk about model discretization. You will often hear this referred to as creating a grid or a mesh to represent the model domain. This figure on the right shows a mesh or grid overlaid on top of our model domain. So specifically, a finite element mesh is a partition of the model domain into simple geometric objects, or elements, where those elements are a combination of nodes, edges, faces, and the relationship between them. Shown below here are a couple diagrams to help you conceptualize what we mean by each of these terms, as they will come up throughout this session. We'll start with the simple diagram of a singular 2D element or cell, such as might be part of a triangular mesh that you would create. And each 2D element or cell is composed of edges, nodes, and faces. Your mesh would be composed of many cells connected together along their edges and shared nodes. So once we have an understanding of the 2D mesh, this concept can then be expanded into the third dimension when we introduce the vertical component. Highlighted here in green, we have an example of a singular 3D element with its 8 corners defined by nodes. The nodes are laterally connected across the domain in sheets, as you can see highlighted in orange, and the 3D element volumes are laterally connected in layers, as you see highlighted in yellow. HGS can handle both 6-noded such as this, and 8 noded 3D elements in its solutions. In our general practice, we most commonly use the 6 noded elements based on a 2D meshes with triangular elements, as this allows us a lot of flexibility in terms of the model discretization and following all the input features more closely. So just here, when we're talking about meshes and grids, there are two kind of main overarching types that all grids would fall into. That is either a structured mesh, where all cells are the same size, at least within a row or column, and are aligned in the same direction. Any cell in a structured grid could essentially be identified by its IJK index if we were to assign that, and then neighboring cells could be identified by adding or subtracting from that index. This is in contrast to an unstructured grid, where we would not be able to do this. These meshes allow for a wider variation in the shape, size, and orientation of the elements, and ultimately much greater flexibility for accurately discretizing real-world features. So here's a quick side-by-side comparison of a discretization of a few input features. Here we have some input geometry of a polygon represented by this green area, a streamline feature running through the middle, and then a few isolated well points throughout our model domain. So while this structured grid is very easy to set up, notice that the elements of this grid, so each of these regular squares, often do not align well with the actual edges of our polygon, as well as our streamline feature, and the points are often not centered in our cells. If we compare this to our unstructured grid on the right, in this case, this example is showing a Voronoi type grid. This grid used these features as part of its input when it was created so that we can ensure that the cell centers are aligned along the edges of the polygons and lines, and that the points are centered within our cells. Another advantage you can notice here that we can choose to have smaller cells in the areas that we are most interested and larger cells in those areas that we are not as interested in. So overall, this means that unstructured grids have some fairly significant benefits, being that you can follow important geographic or geological features, refine more heavily in areas that are more important, while simultaneously reducing resolution in those less critical areas and aligning cells along any preferred flow paths. So see on the right here, there's a couple triangular grids that incorporate several different input features and zones with a highly variable cell size. So, however, these unstructured grids are much more difficult to create, so that requires the use of some additional tools to assist in this grid generation. That's really where AlgoMesh comes into play. AlgoMesh is a Windows-based GUI software tool that allows you to quickly generate high-quality triangular meshes with lots of flexibility for those input features. You can directly import point, polylines, polygon geometry from common GIS and CAD file types to act as controls in your mesh. Most importantly, AlgoMesh is fully integrated with HGS, allowing you to export HGS model inputs, including your mesh file, selected nodes and elements, which are your nchos and echos files, as well as some shape files of the cell geometry and node locations, which are often quite useful. AlgoMesh includes two algorithms available that you can choose to use for creating your mesh. That's Delaunay refinement and a multi-level optimization. Delaunay refinement can generate meshes quickly and provides a hard guarantee on minimum angles in the triangular elements themselves. And the meshes produced by this algorithm are a reasonable quality, but often have some unnecessary variation in cell shape, as well as more nodes overall than might be optimal. The multi-level optimization, it does take longer to produce a mesh, but the meshes produced are much higher quality with fewer cells overall. So it's important to note that the optimization does not provide guarantees on a minimum angle within triangles, which is why it is good practice to run a Delaunay refinement even after creating an optimized mesh. Here's a side-by-side example of a mesh that was generating each of these two algorithms with the same input geometry. So notice on the left here that the Delaunay refinement produced a mesh of 4,081 triangles in under a second. This is extremely fast. The cell quality here is fairly reasonable, but there is a bit of unnecessary variation in some of the aspect ratios of these triangles, especially when you compare it side by side with the optimized version. So on the right side, this optimized mesh is much more regular in appearance with a very smooth transition from the smaller elements to larger elements and fewer triangles overall, and fewer triangles with higher aspect ratios. Also notice just the overall triangle count is almost 25% reduction in using the multi-level optimization compared to the refinement. However, notice that the runtime to create this particular mesh was quite a bit longer at over 4 minutes. Now, when you're dealing with a relatively small mesh, such as this one, that kind of difference is not really too much of a big deal, but once you start dealing with larger and more complex meshes, that can really magnify the difference in time to generate a mesh. So now I'm just going to explain how each of these two algorithms work, starting with the Delaunay refinement. So a Delaunay triangulation comprises a set of triangles with the geometric property that no vertex of any triangle is contained inside the circumcircle of any triangle. So when this is applied to triangular grids, this maximizes the minimum angle of any triangle in the grid, thus avoiding poor quality, narrow, high aspect ratio triangles. So in the process of producing a mesh using this refinement, all input geometry is connected in a constrained Delaunay triangulation, CDT, in that it identifies and creates a queue of bad triangles, where bad in this case would be defined by some geometric criteria set by you, the user. This is usually a minimum angle or an edge length. And then each triangle is split in turn by introducing a new point and an appropriate position within the triangle's circumcircle and adjusting the triangulation accordingly. And then this would continue until there are no more bad triangles present, or it has reached the maximum number of triangles as defined by the user. In contrast, the optimization algorithm, which employs a multi-level variational approach to produce much higher quality meshes with fewer overall cells, it combines this Delaunay refinement with a weighted Lloyd smoothing technique to iteratively minimize an energy functional derived from the edge length field. Execution of the variational approach can be broken down into multiple levels. At each level, new vertices are introduced using a limited Delaunay refinement, and then all vertices of the mesh are moved towards their optimal positions according to an energy function with a relative movement threshold is met. The number of vertices introduced at each level, as well as the total number of levels, is controlled by the user through a parameter. So the overall idea is we add a few points, smooth it out, add a few points, smooth it out, and that would continue until we reach our maximum number of iterations and all our criteria has been satisfied. So a little bit of discussion about the edge length field and this energy functional. So the energy function used to determine the optimal relative vertex positions is derived from the input cell sizing field over the model domain. The sizing field itself is generated based on the mathematical concept of local feature size. So this is the function that smoothly varies from smaller values at boundaries where there are many input points, line segments, to larger values in open areas of the model. So this provides a natural grading of cell size from small to large throughout the domain. But it can be controlled by the user both globally through parameters influencing the local feature size calculations, as well as locally, for example, by adding polygonal regions in which maximum cell sizes are specified, or resampling along polyline features such as streamlines with points at different spacing intervals. So here's a more detailed breakdown of what exactly is happening during this multi-level approach. So first, for each triangle, a sizing ratio is calculated. This sizing ratio is simply the current edge length divided by the desired edge length from the edge length field. Ideally, we would want this value to be equal to 1. That is, the current mesh would perfectly match the edge lengths that we desire at any given location. The second step, the initial target sizing ratio is calculated. This is based on the maximum sizing ratio that was found in the first step multiplied by the reduction factor. The reduction factor is a parameter that is chosen by you, the user, and is always a value that is less than 1, so that this target sizing ratio will decrease over time. Then, any edge constraints and triangles that currently have a sizing ratio that is higher than the target sizing ratio calculated in step 2 will become candidates for refinement and will have a point added at the edge midpoint or the triangle circumcenter. Then, this relaxation, the Lloyd relaxation, is performed, which moves the points closer to the desired edge length as was defined in our ELF energy functional. Then we go back to reducing the target sizing ratio by a reduction factor and repeat the steps iteratively until all the constrained edges and triangles have a sizing ratio of less than or equal to 1, meaning that all of our triangles and edges would have edge lengths equal to or smaller than the chosen desired value in the edge length field. And finally, there'll be a final Lloyd relaxation step performed, which will bring our mesh as close as possible to the ELF energy functional within the parameters that we had set. So now that you've had a little bit of a background on how the refinement and optimization algorithms work, let's think about building a mesh. So keeping in mind the benefits of an unstructured mesh, that means that we can build the geometry to closely follow important geographical, geological, hydrological, or any man-made features that might be important to us. Really, any feature that can be represented by a point line or polygon can feasibly be built as a control in the mesh. So what is most important to you is going to be specific to your model in particular. So first things first, it's really important to think about what features are going to be important to you in your model from the very beginning of mesh creation so that you can build in the appropriate node control along those features. This is really almost like the most important fundamental part when it comes to building a mesh, because we need to have some of these features built into our mesh so that we have the appropriate node control at these locations. These are just some examples of typical features that you might want to think about building into your model. This would be the model domain, which might typically be a watershed boundary, but not always. Streams or rivers, lakes or ponds, well locations, gauge locations, water control features. That might be things like dams or levees. Regions of interest that you may want to compare against each other in the future. You would want to build those boundaries directly into the mesh. As well as any geographic areas that have high interest where you might want higher mesh resolution. This is really by no means an exhaustive list. So there could be other things beyond what listed here that you might want to build into your mesh, but that's just going to be particular to the problems that you're looking to solve with your model. So to prepare for building a mesh, we would typically use a GIS software package of some kind to process the input control features, some common ones being QGIS or ArcGIS. Most importantly, at this point, you need to choose a data projection for all the data sets and make sure that they all use the same projection before you bring them into AlgoMesh. We would want to use an equal area projection of some kind. UTM is probably the most common. At this point, you should also be checking that all of your input data sets reflect the features that you want to build in your mesh, which is much easier to do in GIS software because you can compare against maps or air photos more easily. And once you're happy with all of your features, you want to save them as shapefiles so that they can be imported into AlgoMesh. One input data set that you will have to generate yourself is the bounding box. So this is different than the actual model boundary. But it is needed as an input for AlgoMesh. So just on the right here, you can see bounding box compared to what we want as our actual model boundary. One way to create this is to simply draw a polygon feature in your GIS software that completely contains your model boundary, being sure that you leave a small buffer because you just don't want this to be touching your model boundary. Your model boundary needs to be completely within this polygon. There are no hard and fast rules on that buffer distance, but a few meters should really be sufficient to make sure that they don't cross. So at this point, now that you've decided on all your input data, we can move on to AlgoMesh itself. Here we have just a quick overview of the layout of the software. On the left here, the project viewer shows you all the data sets that you might have imported. Below that, you would be able to see your node and element counts for your current mesh that you're building. In the center, we would have the actual mesh viewer where you can see and interact with the data that you've imported and the mesh that you build. And on the right, we have the actual mesh generation panels with 2 tabs, one for refinement and optimization, as well as a log panel, which keeps a history of some of the actions that you've performed. So there are 3 main types of data that we'd be importing to build a mesh. The first being the bounding box, which encloses all your input data. The second being spline sets, which are control features on the mesh geometry. This includes your model boundary as well as any point line or polygon features for which you want to create control nodes at their location or along their edges. And the third being property polygons. These are areas for which you want to define greater mesh resolution within their bounds, maybe not just necessarily along their edges. So the first step in any mesh build is always importing the bounding box. This is done from the top toolbar under File, Import Mesh Geometry. And that's it, simple. Spline sets, aka any of the geometry features that we want to have as controls on the placement of our nodes. Those are imported on the left side panel by right-clicking on spline sets and importing the GIS polylines as splines. Don't be thrown off by the polyline terminology in this menu because you can also import points and polygons here. You can import as many spline sets as you want into your project. So you can see here that we have imported some spline sets into our viewer. In this particular case, the 2 spline sets were imported, one being the model boundary and the other being some roads. The vertices of our input data sets show up as these yellow squares. So those would have been the vertices that were part of the actual input shapefile, and then the segments connecting them, our edges, show up as orange edges. So once we've imported some spline sets, we have this kind of optional step where you can set some custom edge lengths along those spline sets. You don't have to do this if you don't want to. You can opt for using the more global settings during optimization if you prefer. But doing it this way allows you to set different parameters for each spline set, so it offers a bit more flexibility. To do this, you would right-click on the desired spline set in the left panel, and then set properties for all splines in set. Select a sampling type and modify both the start and end values to a new value. An important note here, if you are changing these values, you probably want to keep a record of these values that you changed somewhere, because if you close this menu and reopen it, it does not show you the values that you had previously input. So here's a note on the 2 different sampling types that you can choose in this menu and how they operate a little bit differently from each other. So on the far left, we have a spline with no sampling along its edges. The mesh nodes just use the original vertices as the control points. You can see these 2 yellow points here. If we choose per segment sampling, as shown in the middle, it will resample between each of these vertices, and it will keep the original vertices in place. The third type, the per entire spline sampling, where the entire spline, it takes the entire length of each spline and splits it according to your sampling interval, and would only honor the location of the original endpoints of the spline, not necessarily those vertices in between. So this entire spline sampling wouldn't typically be used in this particular situation where we're trying to add additional control points along a straight segment. It's much more useful in the case where you have a highly complex input where you're trying to simplify it somewhat. So our third type of data are importing our property polygons. To do this, we would go to Property Polygons in the left panel and choose to import GIS polygons. So if the property polygon does not already contain the edge length property within its data fields, you can right-click on it, on the name of the polygon you've just imported, and choose to add a new property. Name this property something appropriate and enter your desired value. So we've created this property now, but we actually have to apply it to be used as an edge length constraint on our mesh. So after it's been created, or if it was already present in the input file's attribute table, we can use it as a constraint on the cell edge length. We would just right click on the property itself and map it to the mesh variable as overlay and choose mesh cell edge length. So moving on from data import, we will head on to setting up our mesh boundaries. So after importing the bounding box and the boundary spline, you can set your desired sampling interval for your boundary. Just here we've chosen a value of 5, and you can kind of see here how it resampled some points along each of these segments in between the original vertices of the boundary. At this point, we have two options for setting up the boundary. One is to permanently add the boundary directly to the mesh. You can do this if you're certain about your mesh boundary and the sampling interval, or you can run an initial refinement without permanently adding it to the mesh if you want the ability to potentially edit the mesh boundary or the resampling interval at a later point. Can you note you always have the ability later to kind of bake this into your mesh at a later point, so you're not so choosing it to be editable at the beginning can maybe give you a bit more flexibility in your mesh creation. So I'll just show you how to do each of these two things. So in the case where we're permanently adding it to the mesh, we would just right click on the boundary spline after we've imported it and choose to add to mesh now, and that deactivate set and original mesh and generated mesh, which will then create something that looks like this. You can see the boundary has been connected through each of its resampled points to the actual bounding box. In the second option, where we're not permanently adding it to the mesh right away, we would instead go to the Refinement tab and just click Refine Mesh. At this point, you can just leave these default values as is, and then you should get an output that looks something like this. So in both of these cases, you would notice that triangles were created outside of our desired model boundary. So in both cases, we have to deactivate the region outside of the model boundary. So to do this, first make sure that you're in the edit mesh mode. So at the top, you would click on edit and make sure that edit mesh is what is checked. At that point, you can simply click on any of these triangles that fall outside of the model boundary. Once you've clicked on one, it should turn blue. And then you can press the minus key on your keyboard, and that whole area will turn kind of this grayed out look. And that's letting you know that this area is now deactivated and not part of your mesh. If you happen to make a mistake and choose the wrong area, you can add this back in by pressing the plus key on your keyboard. So now that we know how to set up our boundaries and import the different types of mesh controls, we're going to move on to more of the specifics with refinement and optimization itself. Just as a note on kind of good practice here, it's always a good idea to save your project file before you start playing around too much with refinement and optimization, just in case you run into any issues that crash the software. It's good to just save all your inputs so you don't have to go back and redo that. So here we have kind of a schematic of the overall process of mesh creation. We start with our input splines, triangulate between our inputs, enforcing some constraints along our boundaries, and then run one of our algorithms to produce a mesh. Optionally, you can convert this to Voronoi mesh, but we'll just be leaving ours as a triangular mesh. So starting off with mesh refinement under the Refinement tab, this would be running a simple refinement that will produce a mesh very quickly, but not necessarily very high quality. This would typically be used to identify any potential issues with the geometry, get an approximation of mesh node counts at our desired edge length, and it is also run after optimization to remove any potentially bad triangles with small angles. So I'm just going to highlight here, these are typically the two parameters that we might be adjusting on this tab. That is the minimum angle as well as the edge length. You can see here what kind of effect choosing some extreme values has on the output mesh. It should be noted here that if you do choose a high minimum angle, you might not actually get a complete solution. The maximum viable angle is usually somewhere around 35 degrees, but will vary a bit depending on your data inputs. So having a very low minimum angle, you end up with these extremely elongated triangles compared to, say, something more like 30, 34 degrees, where you get much more regularly appearing triangles. And of course, edge length is fairly self-explanatory. When you have high edge lengths, we have larger triangles. Small edge lengths, we get many more much smaller triangles. So this has a very big effect on overall mesh density. So let's move on to the optimization tab now. This is where we usually spend kind of most of our time when building a mesh. Optimization is what's used when producing a final mesh for export. It takes longer to run, and it can produce very high quality meshes with greater control over varying mesh resolution throughout the mesh itself, and overall lower cell counts compared to refinement. So starting with this top section, the first section of this tab, you have the controls for the automatic generation of the edge length field. So this edge length field will be using your input point and line geometry and constraints on cell sizes to create the ELF. The computed ELF is an approximation of local feature size. The cell size at boundaries depends on proximity to other boundaries and is limited by user-specified cell constraints. It's constructed as a tin comprising resampled points along boundaries and points in a regular grid over the model domain. And cell size gradually increases away from boundaries. So let's dive in a little more deeply with some of the options that we have here. Starting from the top, we have the distance grading factor. So this controls how gradually the cell size increases away from the boundaries. Adjusting it determines how quickly the size of the triangle changes as you move away from a boundary. Small values have very slow changes, and high values have very quick changes. So you can see here how this affects the overall density and quality of the triangles in our final mesh. Many but higher quality, aka more regularly shaped triangles on the left, and fewer but more irregularly shaped triangles on the right. So the default value here is 0.4, which is usually a pretty decent trade-off between overall cell count and the quality of the triangles. Next, moving on to the boundary feature size factor. This controls how many cells are generated along the boundaries of a mesh domain. So the sizing of the cells along the boundaries is always dependent on a combination of the spacing of the input points, as well as the distance from one boundary to other nearby boundaries. But the boundary feature size factor acts as a multiplier on this. The recommended range is from 0.5, where you would have many smaller cells along boundaries, up to about 0.3, where you would get fewer, more elongated cells along boundaries. The default value is 2. What you want to set this as is kind of dependent on your model. You can see kind of in this example here, if we didn't want to have these elements connecting across between these two input splines, we can see that a value of 2.5 is too high for this mesh. So something closer to 1 gives us enough separation between each of these input boundary lines. So next we have the number of grid samples. So the edge length field generation process produces a tin with a combination of resampled points along the mesh domain boundaries, the intermediate points between boundaries, and then regular grid points. The target mesh cell edge length values are calculated at each one of these points. So this setting controls the number of regular grid points that are used in this process. So higher values for this setting will result in more resolution in the property tin, but it also increases the memory and space requirements of your model. So for example, if two constrained cell sizes are quite close to one another, the default resolution might not be fine enough in order to increase the cell size in that empty space between these two areas. And you could end up with a strip of, I guess, over refinement connecting the two areas, where increasing the grid samples could eliminate this problem. But in most cases, the default values work for most meshes. Next, we have the boundary resampling factor. This controls how finely the boundaries are resampled for computation of local feature size in the edge length field generation process. This is a factor of the boundary line segment length. Smaller values will result in over-refinement along boundaries, particularly near tighter angles or in areas of congested geometry. Higher values may mitigate over-refinement along boundaries, but the resulting mesh should be checked to ensure that cell quality has not been compromised as a result of this. So the recommended range is usually somewhere between 0.25 and 2. The default value is 0.5 and works for most cases. This minimum sampling resampling interval, if you enable it, places a constraint on how finely the boundaries are resampled. So it's an absolute minimum distance between resampled points and has a pretty similar effect to the boundary resampling factor. So this value is dependent on the spatial scale of the mesh domain, but by default, this is turned off. So these next 4 settings adjust which edge length constraints are actually honored during the edge length field generation. The edge length at constrained points will apply to any point type splines that were imported. So note that for points data sets, a custom edge length cannot be set for the individual data set in the same way that it can for polyline inputs. So this is especially important to have checked off if you are importing something like well locations where you might want additional refinement surrounding the well. This is a global setting, so it would apply to every point type data set that you have imported. So if you have a more complicated situation where you have multiple points data sets and want different edge length controls around each of them, then I would recommend using property polygons to set different edge lengths in kind of buffer zones around your wells instead. So the edge length at constraint edges, this will apply to any cells that are touching polyline types that were imported. Again, this is a global setting applying to all input lines. What I would generally recommend setting edge lengths for each imported spline set instead. But do note that if you have set a custom edge length for your individual splines, those will be enforced if those custom values are smaller than whatever value is indicated here. So these next 2 boxes are quite important to have checked off if you have imported splines with property polygons for which you've set values. If you do not check these off, then those custom values will not be honored in the edge length field generation. An important note about this last box, if it's the first time that you are generating a mesh in your project file, i.e. no edge length mapping field has been created yet, you need to make sure that you either check off to auto-generate this at start of optimization, or that you physically click the generate edge length property tin button before you move on to trying to optimize the mesh. Because if you don't do one of these 2 things, the software will crash when you start your optimization. So it's another reminder and good reason to make sure that you save your setup file before playing around with the optimization settings. So now that we're done playing with the settings that would affect the edge length field generation, we're going to move on to the optimization settings. Here you can make some changes to set a global maximum edge length, adjust the quality criteria for each iteration of the optimization, and set limits on the overall number of iterations. Here we have the global max edge length, which sets a maximum edge cell length that would apply to the entire mesh, not just where it is constrained by some input splines. So as you can see from this field can make a pretty big difference in your final mesh cell count if we compare, say, 25 meters to 10 meters. Just a note on this based on user experience. We would want to increase this edge length by, say, approximately 30% or so to achieve the actual edge length we want. So for example, if we are looking for a maximum edge length of 100 meters, we might want to set our global max edge length at 130 meters instead. So for example, yeah, so this kind of has to do with how the optimization algorithm functions, where the optimization will stop once the sizing ratio is at or below 1. So since we aren't usually dealing with perfectly shaped triangles, raising this limit a little bit higher than what we actually want results in a final mesh that is closer to that actual desired edge length value. And this would apply for not just the global edge length, but also when you're using polygons to set edge lengths for regions. So the next step here is picking a quality preset. There's really rarely a reason to adjust any of the values other than choosing the actual quality preset itself. You can see here on the right, two meshes that were produced from identical inputs. Both of them are actually pretty good. Certainly even the low quality optimization produced a pretty good mesh. It's better than what we could get with just refinement alone. But you can see how there's more regular cell arrangement on the mesh on the right compared to the lower quality one. And overall, there are fewer triangles in the higher quality mesh in addition to this more regular arrangement. So in this panel, you can also set some maximums on the number of iterations. Typically, a run will complete without setting any maximums, but sometimes an iteration can kind of get stuck between a couple solutions, and setting some maximums here can guarantee that the optimization should proceed forwards. Here we have presented a workflow kind of based on some internal user experience to help avoid the optimization getting stuck if we're trying to run that final high quality mesh without any limitations on the number of iterations. So we found that if you start by running a limited quality 3 mesh, where all 3 of these iterations have been limited to some value, let that complete. Then run a high quality optimization with just the Lloyd iterations checked off. And then once that is complete, then you can run a high quality mesh with all of these not checked off. And that should, at that point, helps kind of, there's some kind of like internal memory that happens with some of these optimizations. So doing these 3 things can help in the situation where this unlimited high quality mesh is getting stuck. So last set of settings that we can adjust here are post-optimization settings. So typically we do run a Delaunay refinement on a mesh after that the optimization is completed. So if you have these checked off, this will just run automatically on its own. You don't have to click anything extra to get it to run. So you can set what your desired minimum angle is here, and it will remove any remaining small bad triangles that might still be in your mesh. So in this last section, we're going to be covering a bit how to do some manual editing of some import data in AlgoMesh. So splines, they can also be created and edited directly within AlgoMesh itself, not just, it doesn't all have to be done in GIS software ahead of time. So if you have some small edits that you want to make that are easier for you to do here, you can do that. So to edit splines after you've imported them, you need to make sure you're in spline editing mode. So something to be aware of before we go into the steps here, there's no undo button when it comes to editing splines in AlgoMesh. So if you are wanting to return edited splines to their original exact location, you would have to remove them from your project and then add them back in from their originating file if you needed to return to that. So always a good idea to save before you're doing any manual edits. So this here shows you how we might edit an existing vertice of a spline. You would simply just click on it. Once you've clicked on it, you would see that the spline is active. It would turn yellow, and then you can simply just drag and drop any of these vertices to a new location. You can also add completely new vertices to a spline just by holding the control button and then clicking on one of your segments. The existing segment will turn yellow to indicate that it is being snapped to the existing segment rather than adding a point next to the segment itself. So that's what we see here. This point has been snapped and is now part of this spline. Also be quite useful to extend existing splines. So you would do this by clicking on your end vertice, holding both Shift and Control at the same time, and then wherever you happen to click would then add a new vertex and would connect it along a segment between those two locations. Similarly to editing splines, we can also edit the mesh itself. This can be useful if you just need to add, say, a couple of nodes to your mesh. After optimization has been run, you notice it needs a little more information or a little more resolution at some specific spots. You don't have to completely run your optimization again. You can just add some points exactly where you need them. So to enter editing mesh mode, it's the same thing. You go to the edit menu, make sure you're editing the mesh. Also save before you make any manual edits at this point. The controls here are pretty similar to the way that you'd be editing a spline. If you hold Control while clicking on a spot on your mesh, it would add a node wherever you have clicked, and then the mesh elements would rearrange themselves to accommodate each of those new nodes that you clicked to add. Important to note here that since these nodes have been added directly to the mesh, they cannot be removed and they will stay in place even when a new optimization is run. So if you want to have a manually editable set of nodes instead, you would create a new spline set to hold these nodes, and then you can manually add those points to the spline set first. Then once you're happy with them, you can save it, and then you can add that spline set to the mesh instead. So that gives you a little more control if the points you've created don't produce exactly the result you were hoping for. You can go back and change that. So next, once we have created our final mesh, we need to evaluate the overall quality of our mesh if it will be suitable for use in HGS. The two most important factors to watch out for are very high aspect ratios, meaning thin elongated triangles. High aspect ratio elements can cause numerical instability where the solution fails to converge, as well as very small elements which unnecessarily increase the node counts and thus the runtimes for our models. Quite often, bad triangles or areas of over-refinement are fairly obvious, even just when visually inspecting the mesh. However, there are a few quality metrics that are available to us, both within AlgoMesh and HGS itself, if we want kind of a more quantitative look at mesh quality. So these are the tools that are available directly within AlgoMesh. If you want some quantitative assessment on mesh quality here, they can be found if you go to the top menu under Mesh and then Mesh Quality Metrics. So we'll be taking a look at each of there's 4 different quality metrics that AlgoMesh has available to us. So once we click that, this window will open up within AlgoMesh. And there's a drop-down menu here where you can choose from the 4 different quality metrics to view. Generally speaking, all of these metrics, we're looking for higher values or values closer to 1 being better, and overall smooth distributions of these quality metrics. So the first option is the normalized bisection deviation from centroid. This property mainly pertains to meshes for mod flow, and it's just a measure of the extent to which the flow paths between neighboring cells are not perpendicular. Next, this one's probably the most useful to us. We have a reciprocal aspect ratio. This metric is calculated on the Delaunay triangulation, and for each cell, the quality is the ratio of the shortest side to the longest side. Again, higher values are better here, and a smooth distribution would indicate regularity in the distribution of the shapes of our triangles throughout the mesh. The final two quality metrics are both quite similar. These are the normalized in-circle to circumcircle radius and the normalized area to side square ratio. Both of these are also based on the Delaunay triangulation. The in-circle radius to circumcircle radius is a ratio of these two radii normalized to fall within 0 to 1. And the area to side square ratio is the ratio of the sum of the square of the sides compared to the area of the cell. For both of these ratios, values closer to 1 indicate elements that are more regular and less elongated. So any of these quality metrics can also be exported to CSV or shapefile if you're having trouble finding the actual locations in your mesh that are of poor quality. So you can see here on this graph, it's a bit hard to see, but there are some pretty poor quality triangles as indicated here on the quality distribution. So if you, say, exported the shapefile along with this quality data, you could quite easily find those triangles which have these poor quality aspect ratios. And this, in our latest version of HGS, it also includes some built-in mesh quality assessment tools. So I would really recommend checking this out. The following table here shows all of the different metrics that can be output in the echo file, as well as describing what are the acceptable ranges for each of these, as would be described in the file output by HGS. So next I'm going to go over how to create NCHOS and ECHOS files. So this is something that you could do in AlgoMesh after you have created your final mesh. This allows you to select and export specific elements or nodes from your mesh. So yes, very important that you do this for your final mesh, because regenerating a new mesh means that you would need to remake these files because it is tied to that specific AH2 file. So these types of files are typically used to build and alter your HGS model. NCHOS files are node selections, and they are usually used for point or line features for things like wells, streams and outlets, hydrographs, engineered walls, fractures, boundary conditions. And ECHOS are your element selection, and these are applicable to area features. This would be things like a riverbed liner, a lake, or soil line geology, anything that you would really want to adjust parameters in your final output or your final model. So NCHOS files, you would just go to select and select triangular nodes, and then you can select single nodes by clicking on them in the view. If you want to select more than one in a single selection, just hold Control, and then you can click on any singular node. If you want to select all in a row, you would hold Shift while doing the same thing. And it would connect along the shortest path between the first one you clicked and the last one that you clicked. ECHOS files, it's the same idea. You would turn on to select triangular elements, and then you can select your triangles by clicking on them in the view. And the way that you would do that is exactly the same as for selecting elements. It's Control to select more than one, and Shift to connect along the shortest path between your first and your last element. So once your selection is finished, you can save the selections to your eachos or entros file. Make sure that you always type the actual file extension into the file name because AlgoMesh doesn't do that for you. You can only create one selection file at a time, but you can also load in existing selections from this menu, load selection, and add to it if needed. So another important note, if you edited or resampled your input splines, you might possibly want to export those edited files for future use in GIS software. So you would right-click on the spline and export those splines as GIS polylines, and this would export a file from AlgoMesh. So important to note here, any files or spline sets that you export to shapefile from here are not going to contain all of the attributes that your original input shapefiles had. So if it is important to you to have those attributes in your shapefile, would recommend editing your files ahead of time in GIS so that you don't have to make any edits to them within AlgoMesh. And finally, our mesh can be exported to AH2 for use with HGS. Just File, Triangular Mesh, and export our 2D mesh to HydroGeoSphere. You can also export the mesh to be used in GIS software by exporting the cell geometry, which would be the actual polygons, or the vertices, which would produce a point dataset. So this last section is just kind of a little tips and tricks for a kind of data preparation. So kind of a specific example of something that would be fairly common issues that we might run into when processing input data for use in AlgoMesh. So here we have a typical stream network file. So we import that in and we can see that it has an extremely dense number of vertices on this data set as well. These vertices themselves are not on regularly sampled intervals. So in order to generate a clean mesh with reasonable node count, we would often need to simplify this line file before optimization. So where possible, it's best to use GIS tools to simplify these features, but some simplification can also be done in AlgoMesh. So I'll show you how to do that. To do the simplification in AlgoMesh, we'll be using the workflow that was presented earlier where we set properties for all splines in the set. So see here, we set a sampling distance along our spline of 100 meters. Once you specify the sampling distance, you notice that small white dots will appear at our requested interval, and these will be used in optimization instead of the yellow ones that came with the shapefile. So there are some potential problems that can pop up when we do this. We have to watch out for. So to ensure we don't deviate from the original location of junctions, we need to make sure that the vertices at these junctions are snapped together at the terminal vertices. So that's these three segments. If they're not snapped, we can get something like this, where the refinement creates this crazy bullseye of astronomically high node counts at this location. So in GIS, we can modify these junctions. Make sure you could just enter an edit session, make sure you have snapping enabled, and simply snap these together. You could also do this if it's only a few locations. You could also do this in AlgoMesh using the spline editing tools. Another problem that can also pop up, this itself is not a snapping problem. These are actually snapped together. However, the problem here is that this segment is not split at the actual junction location. So this is one continuous input segment, and this is a separate one. So this is something, say, that could happen at your boundary, where your streams meet your boundaries, something along those lines. So what happens when it tries to create the mesh is these two locations were sampled, but since there was no endpoint here, this point was not maintained for this larger segment. So we end up with this crosscut where we have this little extra bit sticking off the end. So to fix this, easiest way is to split and cut this river at the junction so that there is an endpoint at this location for this line. Alternatively, you could also dissolve this together into one feature, and you can explode that again to break the lines at junctions if you want to. Another common problem that we'll see coming up are where there's small overshoots or undershoots. The trimline tool can be quite useful for fixing these. You can get rid of small dangles in your data set. If you don't have access to some of these GIS functions, you can try using the clean geometry function in AlgoMesh. That can also get rid of small segments. You would just set a threshold within this tool, and it would attempt to clean those lines for you. So really, in summary, a spline should be as clean as possible before import into AlgoMesh, and definitely before starting optimization. Yeah, I personally would recommend that all polyline control features are merged into one spline set and processed beforehand, potentially even including the model boundary in this spline set. That's the easiest way to ensure that you don't end up with these issues. So here we have our final cleaned river data set. So you can see the property 10 that's generated is only at the sampled vertices, and it has sampled this junction location. We run the optimization, and we get a much cleaner mesh than before we fixed up this geometry issue. So this is what you can expect a good mesh to look like when you have clean input geometry. So really that example concludes this basic introduction to AlgoMesh and how to build a mesh suitable for use in your HGS models. So I'll take some time now to answer some questions from the chat, or if you have any other questions to ask before Braden will take it away.
Hey, Amanda, this is Braden. I haven't seen any questions in the chat so far. But why don't we just take a minute here before we go into the tutorial, and if anyone wants to unmute themselves and ask a question directly to Amanda, that would be fine. I think George had his hand up.
Yep, I have a question. Is it possible to select elements that are inside a polygon? For example, if I want to select some nodes that are inside a polygon I created in ArcGIS, can I select all of them?
You would have to. The way that I would approach that, I wouldn't necessarily be doing it directly in AlgoMesh. So with your kind of exported mesh file, you could get the node list in GIS to select those elements, and then import that as a text file into AlgoMesh for those specific element numbers.
It is actually possible to select all elements and nodes within a polygon. Yeah.
Oh, okay.
I'll demonstrate that in the tutorial.
Oh, perfect. Yeah.
Yes, and I was trying to do a mesh, and I don't know if it's the same question, but I wanted to select all the nodes that were along the boundary, except the ones that are downstream. Is it possible to do that? Just select some points in the boundary, but not one by one, instead of that in a group?
There would be a couple of ways to do that, I think. And again, we'll demonstrate that a little bit during the tutorial, but the easiest way to select all the nodes along a particular stretch would be to import a polyline that goes along that area that you're interested in selecting. If you import a polyline that delineates the entire model boundary, then you can right click imported objects and use the select along polyline option. So, but that would select all the nodes for the entire model domain if it was, defined as using one single polyline. There is always, of course, the ability to mix and match the different techniques as well. So you can use a polyline to select all of the, all the nodes along the boundary, and then using, I think, control, if you hold control, you could then deselect some of those nodes. So you can mix the manual as well as the, the shapefile informed selections. But of course, if the polyline, if you're wanting to select all the nodes along a polyline, it's not going to select nodes in just one region. It will select all of the nodes along that polyline.
Okay.
So if you wanted to select only the nodes in a particular area, then just create and import a polyline specifically for that selection.
Okay, thank you.
Yeah, I see a question from Jiang Yu.
Yeah, I have a question. So if we import a stream into AlgoMesh as a spline sets, and let's say it's problematic, can we just, like you said, can we just convert it into a polyline and resample it in AlgoMesh? Is that easier?
Yeah, I guess you can do that in AlgoMesh. Yeah, just the only thing you have to be aware of is if you need that streamline in the future as a shapefile or something like that, it wouldn't have all the attribute information from the original data set associated with it anymore. But if that's not necessarily important to you, it's definitely easiest to just do that simplification in AlgoMesh using the resampling and potentially the clean geometry tool.
Okay, thank you.
Yeah, I think, as Amanda said earlier, best practice is generally to clean up all of your imports in GIS before you even import them into AlgoMesh. But once they're in AlgoMesh, there's always options. Okay. Well, I'm not seeing any other questions coming in right now, but I think for the duration of, or the rest of this training session, it's going to be a little bit hands-on. I'm going to share my screen now. Steal it away from you, Amanda. And the first thing I'd like to do is just kind of introduce some of the training materials that we have available to us here. So in the course package, I've included 2 tutorials as well as a PDF of the slides that we've just gone through. Tutorial 1, I'm going to work through with you right now, and I encourage you to just sit back and watch me as I go through it. It's not going to take very long, and we'll certainly have some time left over at the end of the session today for you to work through these tutorials on your own. And of course, we'll still be here to answer questions as well. As I do work through this this tutorial, feel free to interrupt me. I think it's good to address questions as they come up in this kind of interactive portion of the tutorial. Now, tutorial 1, which is the one I'll be working through, this is actually it's our comprehensive introduction to HydroGeoSphere tutorial. But what we're going to be focusing on today is part 2, building the model mesh in AlgoMesh. I'm going to work through the whole AlgoMesh section, and I'll also highlight how exactly the exported model mesh as well as the exported nchos and echos files can be used in your HydroGeoSphere grok file. If you don't know anything about HydroGeoSphere, that won't take a large portion of the session, but I do want to put the AlgoMesh work into the context of the greater work that we do at Aquanti, which is of course modeling with HydroGeoSphere. So yeah, this is quite a lengthy tutorial, but really it's just part 2 that we're going to be focusing on today. And it's about a 10-page section of the tutorial. Something I will point out here in the tutorial documentation is that if you see a little hand like this means you should be clicking or doing something. So we'll set that aside for now, and I'll point out that the second tutorial that we've packaged up here, this one actually comes directly from HydroAlgorithmics, the developers of AlgoMesh. So the layout of this tutorial is a little bit different. The document's not quite as long. It touches on developing basically a grid for a ModFlow 6 model, so or rather a ModFlow USG model. So you'll see in this tutorial the end result is a Voronoi grid. However, inherent to every Voronoi grid in the background, as we'll see later on, is a triangular mesh. So this kind of tutorial, following along here, we're basically, whether we're generating a mesh for HydroGeoSphere or whether it's for ModFlow, a lot of the same processes and kind of we're going to be following along with the same process basically. Okay, so without any further ado, let's just go straight into the tutorial. So obviously we've got AlgoMesh opened up here. The first thing that you'll always want to do when you're building an AlgoMesh mesh is to import the bounding box. Actually, you know what? Before I go too much further into things, this HydroGeoSphere tutorial that I'm going to be working through, inside the training, inside that folder, we're going to find the tutorial document itself. We're going to find all of the input files for this AlgoMesh portion of the training or of the tutorial. And then in this R5 model folder, we'll find all of the HydroGeoSphere input files, but there's also a folder here called Mesh. And this Mesh folder contains the finalized or the final mesh project. So what you can do if you're interested in just jumping straight to the end, you can always just open up this this AlgoMesh project file, and we could get basically a preview of the end result of this tutorial. So I'll just double click that right now, and okay, I'm going to have some visualization issues here. There we go. So this is basically the end product that we're working towards. So again, I'll set that aside for now, and I'll just reiterate that all of the input files are located right here in the AlgoMesh data files folder. So as I mentioned a second ago, the first thing that we need to do with any AlgoMesh project, with any mesh that we're going to generate, is just import a bounding box file. This, again, as Amanda described, this isn't really an input for the mesh itself. It's simply a box that will encompass the entire mesh domain. You can create that in GIS, or if we open up the file itself, we can see that it's quite a simple file. It just contains 4 coordinates here, and so you could very easily just create this file using Notepad. To import this file and get started on our project, we click File, Import Mesh Geometry, and we're going to select the bounding box.xy file, open that up. So again, this bounding box is large enough to encompass the entire model domain, but once we import the actual boundary of our mesh, we'll see that it doesn't intersect at the corners at all. It's large enough to encompass the model domain, but not small enough to actually intersect with it. So the first thing that we're going to do to get set up here in our project is import all of the spline sets that we're going to be using to inform the mesh generating algorithms. So to do that, we just right click here, Spline Sets, and we're going to import GIS polylines as splines. Now the first one that we'll import here is our outer bound polygon. So this is, as we'll see if we click open here, this is the outer edge of our model domain. We talked earlier about how there's kind of 2 approaches to how you would incorporate this into the mesh. We can actually refine the mesh right now just by clicking Refine Mesh here in the Refinement tab. if we want to follow along more closely with the actual tutorial, what we're going to end up doing is we're going to bake this into the mesh itself. So this basically takes all of the vertices of the spline, and like right now we can right click and access spline settings, for example. We can change the spline type. We always recommend keeping it with linear though. And we can change the edge length at start and end. We'll just put in some values, random values here. And if I click apply to all in set, then we can see that a few of those white vertices have been added. So again, this makes sure that we've got at least one vertex every 50 meters along the spline. Let's drop that down to 10 meters actually. So now these all of these yellow and white dots, or rather just I believe it's just the white dots, we can bake those into the model mesh. So to do that, we're just going to right click this outer bound polygon under the spline sets, and we're going to add it to the mesh now. So as you can see, what that does is it takes all of the splines and all of the added vertices that we've kind of added to the spline set. So all of those yellow and all of those white dots, they actually now become hard-coded points in the model mesh itself. Now, actually, what I've done here is probably not the best because there's a lot of nodes that are quite close to each other. And so once we actually start to refine this, we're going to see that there's kind of uneven refinement along the edge of this, along the edge of the outer model domain. So that's possible. Okay, so what's happened now is it's resampled this line based on, I think, the distance between all of these vertices. In any case, I'm getting ahead of myself. What we're going to do next is, now that this has been baked into the model mesh, is we can remove the area outside of the model domain. Again, just by clicking on any of the triangles outside of our actual model mesh and hitting the minus button on the keyboard. If we were to accidentally remove this area too, we can easily add it back in just by pressing plus on the keyboard. So that takes care of our our outer polygon, the edge of the model domain. We've got pretty evenly spaced vertices along here. So Amanda, maybe you can chime in. Actually, I've never seen this happen before. I'm kind of going a little off-road in this tutorial right now, but when I clicked Refine Mesh, it seems like only the 10-meter kind of splines have actually been added to the mesh here.
Yeah, that's actually not what I would have expected to happen either, to be honest with you.
So yeah, I think what happened is if we can view and we can turn on, if we make this active again. So it seems like it's basically only following along with the resampled.
Yeah, that makes sense
spots.
actually.
Initially, when we baked it into the mesh, there was a spot for all of these original vertices, but it seems to have been overwritten once we actually clicked on Refine Mesh here. So in any case.
Yeah, I think that's because it was the entire spline sampling versus the between vertices sampling. Right.
Okay, so, well, in any case, we're happy now with our outer edge of our model domain. We've got evenly sampled spline set here. So what we're going to do next is we're just going to start importing some of our other spline sets. So we're going to import, well, we'll just go over them as we one by one here. So first we've got what's called the ranch road. So this is a small catchment, and this is basically a road. And so when we're building our HydroGeoSphere model, we would probably want to apply different surface flow properties to this area. And so obviously we can apply different properties if an element is cutting across the road, like this giant triangle right here. So again, any areas of interest, features including different property zones. We've got another one here that we're going to import, which is the quote unquote location of a clay lens. We want obviously our mesh to follow along these areas because of, that's going to allow us to properly recreate these actual, these irregular shapes in the mesh itself. So the locations of property zones, if they're well known, you're going to want to build those into your mesh. And depending on the size as well, the locations of boundary conditions and hydraulic features, those are definitely going to want to be built into the mesh. Observation wells, it's also very important to include those in the mesh. So I think the last one that we're going to include here is basically a point file. So we've got some additional points here which delineate the location of pumping wells. So we've got 3 examples here: a point, a polygon, and this is actually a polyline shapefile. And each of these can be sampled or resampled as as required. So we might want to, for example, add a little bit more refinement along the location of the ranch road. So again, we're just going to right click that here in Spline sets. We're going to go to the properties window, so set properties for all splines and set. And let's make sure that we've got, node spacing along the entire spline here. Starting, well, actually, why don't we just give a demonstration of this? Well, we can say at the start, we want these new vertices to be 50 meters apart, and by the end, they'll be 5 meters apart. So you can see here, the white dots are, much further spaced apart than they are towards the end of the line. Usually you're going to want to have that, pretty uniform. So there we go. We apply a bunch of new vertices to the spline. We can close that window here. Yeah, we'll just click refine mesh here so we can see some of these, some of these different features are now more clearly resolved in the mesh. We have, a mesh node at the exact locations of our observation wells, which is good. We have, triangles that perfectly delineate our clay lens as well as our ranch road. Now inside this ranch road, we might want to refine the mesh a little bit more in order to better recreate the mesh. Here we can see actually the original spline has been resampled at every 5 meters, and so now the mesh elements that actually, select elements here. So now our ranch road is kind of delineated like this, so it doesn't perfectly follow along with our original spline, and that's because we've resampled the spline and put these new white dots in as the actual vertices of the spline. Okay, so if we wanted to have, smaller triangles here inside the ranch road polyline area, what we can do is we can set, some settings along the edge of this polyline. But if we want to make sure that everywhere inside the polyline has, is more refined, then we would have to use a polygon as a property polygon. So if we're just going to right click property polygon sets here. We're going to import a GIS polygon. In this tutorial, we've included the ranch road element size polygon. If we import that, we see that it, pretty much outlines the exact location of our ranch road, except this is a proper polygon instead of a polyline. Here in the Model Explorer, we can see that, this ranch road element size polygon already includes an attribute. That attribute is called element size. If I recall correctly, I think the element size that's built into here it's just 2.5. So everywhere within this polygon, we have an attribute of 2.5, and this is the element size. So if we refine our mesh here, nothing's really going to happen. That's because we haven't actually mapped this this property to the mesh itself. So to do that, we just right-click the desired attribute, and we're going to map it to the mesh, and we're going to map it to the mesh cell edge length. And when we refine again, we can see now that everywhere inside the polygon, the elements are much smaller based on the element size attribute again, which I believe is 2.5. Now we can actually, as Amanda mentioned earlier, we can add new properties directly in AlgoMesh. So it's, if you don't have an attribute for the polygon itself, that's okay. Just import the polygon. You can create your own element size attribute. Just right click, select new property. We'll drop this down to 1 meter. Okay, so we'll call this, element size _1. And again, we're going to map that to the mesh cell edge length property. And I can't remember if Amanda mentioned this earlier, but the order that these different mapped attributes or mapped properties appear in the menu here really matters. So whatever is on top is kind of what's going to actually control that particular property mapping. So if you have two element size polygons or attributes mapped to the same property, if we click here, we can see nothing has changed. If we remove this original element size mapping, now we've got an element size of mapped here for this is the element size 1 attribute. If we refine it again, now we can see that the changes actually kicked in, and all of the elements within that within the polygon actually have an edge length of 1. So I'm going to just quickly delete that. We're going to go back to our we're going to go back to the default one that we had before, 2.5. So that's our element size mapping. Go refine mesh. We forgot to map it again. So we have the attribute, but we didn't actually apply it to the mesh. There we go. So now we've got properly refined mesh here in the interior of the property polygon. I'll just take a moment here to highlight. I accidentally clicked earlier and created a new node. So if we turn off our property polygons, and maybe we can just focus in on this area here and talk a little bit about some of the manual mesh editing that you can do. So up here in the edit menu, we've got some options. We can edit mesh, we can edit splines, we can edit property polygons. Let's start with editing a spline. So we saw, that we resampled this spline, and we've got sort of a, let's call it redundant vertices there. So what we can do is we can select that just by clicking on it. And I'm actually not 100% sure what's going to happen here based whether or not the these newly sampled vertices will kind of automatically connect the spline here. Well, maybe what we can do is we can scroll out here to the edge, and maybe we can see that we have this a couple of extra little vertices outside the mesh domain. We could select those and just hit delete on our keyboard. What we can also do is if we were to delete this vertices, then it's going to basically delete the entire segment between this, this vertices here and this one over here. So what we can do instead first is create a new vertex by holding Control. And as I hold Control, we can see that there is, a little blue square here indicating that this is the location where a new vertex is going to be added. So ideally, we would snap this right to the exact location here at the edge. And now that we've got a new vertex here right at our model edge, we can just select this one and hit delete. So now we see that the vertex has been removed, but there's still a node here that's been kind of baked into the mesh. So we can actually, if I'm not mistaken, we should be able to remove that somehow.
If you click Refine Mesh, it should disappear.
There you go. So we can do the same thing down here. So again, we're making sure that we're editing our splines. Just hold Control, add in a new vertex. We can delete this one. We can also edit our mesh. So what this is going to do, if we edit mesh, what happens is we're going to basically be adding if I hold Control here and I click anywhere, it's basically adding a new hard-coded node into the mesh itself. So now these, again, I think Amanda mentioned this earlier, but as you make edits to the mesh, be careful of what you're doing because, again, these can't be removed. The changes, there's no undo button, let's say. So just as if you ever do make any, manual modifications to the mesh, just be aware of that. Okay, so yeah, we've basically imported all of our model elements that we're interested in. We've created a refined mesh. I'll just take a moment here to just point out, now that we've got some stuff in the project, point out a few different aspects of the model interface here. Obviously, we've been working a lot in this section here, I think, which we call the project, or the model explorer, the project explorer. So this contains all of the inputs for the mesh itself. The main ones that we're going to be working with, at least in the context of HydroGeoSphere, are spline sets and property polygon sets. Now, if you're building, a model for ModFlow, let's say, AlgoMesh does have a lot of additional capabilities where you can map not only things like element size, but if we look at this, we can map, properties to all sorts of all sorts of different properties that are inherent to a ModFlow model. So there's lots of additional stuff in this Project Explorer that we're not going to really explore too much, like things like property rasters, which you could use to, to inform actual flow properties like conductivity, porosity, and that type of thing. Property tables as well. But for HydroGeoSphere, really what we're doing is we're aiming to just build a high quality two-dimensional model mesh. The rest of the model build all occurs in the HydroGeoSphere grok file. So again, the major one here in the Project Explorer are going to be our spline sets. Each spline is treated independently. We can, access the properties for each of these spline sets, sample them and resample them as required. We can turn them on or off for the, visualization purposes. When it comes to viewing different aspects of the mesh, you can also use the view menu. So we can say we don't want to view any splines at all. Now, the splines may remain active or inactive, but whether or not they're active or inactive is, in terms of the view menu is going to kind of override whether they're active or inactive. So like if we turn on splines again here, only the active spline sets are going to actually be displayed. The other thing, correct me if I'm wrong, Amanda, but an inactive spline set is not actually going to be used whenever we run, I think it's just the optimization algorithm. So here for clay lens, for example, it's inactive, but when we ran the refinement, the vertices along the clay lens were kind of added to the mesh as mesh constraints. So that's why they appear here as these red squares with the blue edges along. Those are constrained edges, and then the dots here I believe they are still part of the constrained edge. If we were to turn off the wells here, we can see that again we've got a red dot here. So this would be a constrained point, and here we've got a bunch of points that have been connected, so these are constrained edges. In any case, if I believe if a spline set is inactive, it means that we could turn on the clay lens, for example, and then we could manually edit the spline and add in a new spline there. And since it's active, when I click refine, it will add that, it basically will add that that new spline into the mesh as a kind of as a hard-coded point. Now, if I was to edit this spline and add in a new vertex here, and then if I was to deactivate it, there's no vertex baked into the mesh here at this point, and the spline set is now inactive. So if I'm not mistaken, if I click refine here, we won't see a new node added here. Okay, that was not what I expected. In fact, it removed all of those splines. So, or rather, it removed all of those constrained points. So there you go. If you want to have, you know, your different features added into the model as it's you know, during the refinement and optimization algorithms, generally just keep them as active here. Now, I'm not exactly sure why, like, what happened there, because, you know, our outer bound polygon right now is inactive, but these we bake them into the mesh. That's the thing.
Yeah. So if you actually click add to mesh, it will deactivate it, but it'll still and it will just it'll show up as inactive, but it will still be part of the map, the mesh itself. But if you didn't actually click to add to mesh, then exactly what you just showed will be what happens when you deactivate it.
Gotcha. Okay, so we'll move along a little bit here in the tutorial, but yeah, at this point we've as I said earlier, we've added in all of the, you know, all of the spline sets that we want. We've mapped element size using our Ranch Road polygon here. There's really not too much else that we can do to help with this. We'll make sure that our wells are active. There's not really too much else that we can do to kind of inform the general stuff that's going into the mesh refinement and optimization algorithms. At this stage, we've got all of our points of interest are defined and delineated. So now it's just a matter of kind of basically creating the best mesh that we can out of these inputs. So that's where everything moves over into the refinement and optimization tabs here. So we've got lots of different properties, lots of different you know, things that you can experiment with here. One thing I'd like to show is, you know, Amanda talked about the minimum angle criteria here. If we were to turn this way down, for example, and click Refine Mesh, we see we've got a lot of pretty low quality triangles or elements here, you know, very, very thin angles. So that's not something that we want. Generally, you know, you can probably start at about 30, and that should work fine. As you start to creep up above 30, this is going to generally give you a better quality mesh. However, you start to see, you know, a lot of extra elements where they're perhaps not necessary. And actually, if we go up above, you know, 35 or so, if I run this at 40, I expect that it's probably not going to actually complete. So what's happening here is it's basically getting stuck in kind of a recursive loop. So if I stop refining here, might actually crash the program. Hopefully not, though. We'll give it a moment. So it's basically, it's got 100 and over actually 1.6 million triangles to kind of display here, which is why it's really slowing things down. Where are these 1.6 million triangles, though? So if we start to zoom in, I'm not exactly sure where we're going to find those all those triangles, but it's somewhere in here we're going to find an area where maybe it's over here. Yeah, so what we're seeing here is basically we've put the minimum angle requirement a little bit too high, and the algorithm is basically, you know, what it does, as Amanda mentioned earlier, is it kind of keeps a list of all of the quote unquote bad triangles, and it just starts adding nodes to split those triangles. And if the minimum angle requirement is too high, what you'll end up seeing is that it just kind of gets stuck in one little area. And as we scroll in further and further and further and further, we can see that it's just basically continuing to refine this one small spot. So when it comes to the minimum angle here, 30 degrees is probably a good place to start. And if you want to try and go for a bit of a better refinement before moving into the optimization steps, you can put it up a little bit here, but I would do that incrementally, and probably don't go much higher than 35. Otherwise, you end up in a situation where you get millions and millions and millions of triangles, which is not what you want. Obviously, when it comes to modeling, having fewer nodes and fewer elements is better because that's fewer spots that the simulation actually has to solve itself. So with fewer nodes and elements, we're going to have better model runtimes. And it's certainly worth, I think, worth the effort to try and minimize your total number of nodes and elements within AlgoMesh. Because later on, when you're modeling, you might put in an extra hour trying to refine and optimize your model mesh up front. You'll probably save yourself 10 hours down the road in model runtime. Now, each time that we've refined the model mesh, we can see down here in the bottom right, we also get a bit of a log in terms of what's happening here. So we can see, basically it goes through and it lists with each iteration of the algorithm. Basically tells us what's happening here. So in our previous iteration there, we actually had a total of 1.6 million triangles. If we scroll down now, we've got we refined it from an initial of 808 triangles to just about 6,800 triangles. Now, the total number of triangles in the mesh is also listed towards the bottom of the refinement and optimization tabs. Other settings that are kind of helpful in the refinement tab here is we can set a max area or a maximum edge length for triangles in the entire mesh. So these settings are not specific to any particular object. We've already built in some hard requirements for this spline set, for example. But we can say we want to have a maximum edge length of let's say 15 meters throughout the entire model domain. And if I refine this again, we're going to see a lot of these larger triangles should be split into smaller ones. So that brought us from about 6,800 up to about 7,800 triangles. And this refinement algorithm, it still only took 0.01 seconds. So, making adjustments here and spending some time, working on these things is certainly not going to take you too long. Now, there's lots of other settings here, and I encourage you, once you get your hands on AlgoMesh yourself, to experiment with some of these. But generally, I would say, the max edge length, minimum angle, maximum area, these are probably the ones that are most commonly used. If we switch over to the optimization algorithm now, it's laid out much the same way, but we have lots and lots of extra settings to choose from. As Amanda mentioned during her presentation here, and again, just the same with the refinement tab, there's really only a few here that you're going to want to experiment with, but I encourage you to experiment with all of them, just in the context of learning how to use AlgoMesh, obviously. The distance grading factor, for example, if we were to reduce that, we're going to see that we go straight from very small to very large triangles very quickly. I'm going to stop this optimization right now and change the quality preset to low. And sorry, I had that backwards. If we're going to go from small to large slowly with a smaller distance grading factor. And if we put that up above 0.4, we see a pretty rapid shift from smaller triangles at the constrained edges and at our constrained points, going up to much larger triangles relatively quickly. Now, if this represents, let's say, an observation well, obviously we're going to want to have some refinement around that location. So what we can do is we can apply maximum edge lengths at constrained points and constrained edges. Now, if I turn on the max edge length at constrained points, let's say with a max edge length of 5 meters, we'll actually notice that it doesn't only impact specifically points, but it's actually going to impact, it basically treats not only point objects like this as a constrained point, but it also treats all of the points, I think, within polylines as constrained edges. And maybe I'm wrong. Amanda, am I wrong about that, or?
Which ones do you have checked off? I can't see it on your screen.
Just constrained points. So those would only impact the actual wells, or would that impact all points along constrained edges as well?
I believe it should just be the points, and then the edges would be the next setting.
Okay. Yeah, so this is a global setting. It's going to impact all points throughout the entire model domain. So if you have, maybe you have pumping wells and you have observation wells, and for your pumping wells, you want to have more constrained, a more constrained mesh around the location of pumping wells. But maybe this is an observation well, and you think, well, an observation well can be in a less refined area. Then you would have to basically use a different approach to constrain the points. So these settings here, this for constrained points is a global setting. So if you had multiple sets of point objects that you've imported, this is going to apply to all of them. We can do max edge length at constrained edges as well. So constrained edges would include the edge of the model boundary, and as well as the edges along our Ranch Road polyline and the clay lens polygon. So let's put that up to 5. We'll turn off the constrained points, and we'll turn on the constrained edges. Start that optimization. So again, we've basically added in a constraint to all of the constrained edges throughout the entire model. So that includes the model boundary, it includes the clay lens, it includes that polyline as well. So, there's options to apply global constraints, which is what we're doing right here, but you can also constrain, these elements independently of each other by modifying the spline set itself. Now, modifying the spline set itself doesn't work for points, though. So when it comes to points, you're kind of stuck with either a global constraint or a global option, let's say, for constrained points. Or what you can do, and this is actually covered a little bit in the second tutorial, is you can import a polygon shapefile that basically encompasses those locations, the locations of those points. So you could include a polygon shapefile that includes 4 little polygons at the locations of your wells. So then we've got the boundary feature size factor as well. So Amanda explained how this impacts how refined the mesh is going to be at locations where different boundaries intersect with each other. Let's try and drop this down. We've turned off our global constraints here. We'll put our grading factor back to 0.4 and see what the impact of this boundary feature size factor is. So with a boundary feature size factor of 0.6, which is, whoops, accidentally just modified that spline, so that's kind of annoying. I'm going to turn off edit splines here so I don't accidentally do that again. In any case, so with a lower value of the boundary feature size factor, we can see that where some different boundaries intersect, we're going to have a higher amount of refinement. We'll turn that up to 0.26 and run it again and see how that impacts this area, for example. So here, yeah, as we can see, there's not really any major refinement in this area where we've got multiple boundaries intersecting with each other. And then, yeah, there's a lot of these refinement and optimization settings you can play around with, but again, as Amanda mentioned, as you change the quality presets from low to medium to high, these settings will kind of update themselves, and there's not really any point in specifying, in really kind of altering these values manually here. What you will want to play around with a little bit are the max refinement iterations and Lloyd iterations. So again, if you and there's also these optimization settings to run a Delaunay refinement after completion of the optimization. So we always recommend keeping that checked on. So I guess end of the day, what we're going to do here is just basically run a final optimization. We'll put some of these settings back to kind of their default values. And first we'll run with a lower quality preset. So here, looking at some of the mesh kind of characteristics, we've got 10,620 triangles with the lowest quality preset. If we increase that to, let's say, 3, we're going to see a considerable drop in the total number of triangles here. So we see that it's kind of stuck in a Lloyd iteration here. And we didn't actually specify max Lloyd iterations for the final relaxation, so I suspect that's what's going on here. We'll just stop the iteration. We'll turn on this option, and let's try that again with a quality preset of 3. Okay, we still have about 10,600 triangles in the mesh. So yeah, not a huge improvement from going from quality preset 1 to 3. Maybe if we try a little bit higher, we'll go with the highest quality preset, run that, and see how many triangles we get. So down to 9,000 triangles. So a reduction of about 10% or slightly more than 10%. It still didn't take very long for this iteration or for this optimization to run. So there's definitely, I think, areas where we could probably find improvements here, and again, continue to modify our optimization settings. There's definitely a few areas that are perhaps over refined, like right here. So we would maybe want to revisit the way that the splines have been sampled in this area, perhaps add some vertices, and just kind of continuously iterate on this. We've got maybe more refinement than we need right in these corners here. So there's certainly some, there's things that could be done to improve this mesh. Now, one thing I will note is that as we've gone through here, each time we've made an update to one of the criteria, for example, the maximum edge length at constrained points and that type of thing, whenever we make any changes to these settings, we'll notice that this auto-generate at start of optimization, the edge length property tin, it's going to be generated new each time that we apply a different kind of constraint. So if I turn this on, we can see that it automatically kind of activates this checkbox. Each time I do an optimization now with the new set of constraints, it creates a new property tin here in the Project Explorer. Now, as you continue to make adjustments to your mesh, it's likely that a lot of these you won't really need them. So good housekeeping to just right click and remove any older property tins that aren't necessary at this point. So what else did I want to highlight here in this tutorial before we went on? I think the only thing I wanted to point out is just in terms of mesh selection. So here we can, in the view menu, we can turn on or off different things, edge constraints, splines. We'll turn on edge constraints here. We can turn on or off our property polygons, rasters. So it just makes it a little bit easier when it comes to actually selecting mesh components. Now, to select mesh components and create our nchos and echos files, we're just going to go to the select menu. We're going to select either triangular nodes or elements. And again, here, this is something you'll want to do a bit of experimenting with, but if we select on a single element, we can click around. It's just going to change the selection. If I'm holding Control now, just like a lot of other programs, it's very similar. It's going to add to that selection. If I hold Shift, what's going to happen is it's going to also add to the selection, but it's going to choose all elements between the last point that I selected and the current point. So obviously selecting things manually, though, is going to at times be not the best way to do it. So you'll recall that this was imported as a spline set. We could also import this as a property polygon. So if we import the clay lens location as a polygon, what we can then do is we can right click and select within polygons triangular elements. So that was a question that came up earlier. Very quick and easy way to select, a large number of elements based on, a polygon. We can also do the same thing along splines, although splines will not allow you, splines, they can be points, polylines, or polygons, but I think in the context of AlgoMesh, splines are kind of all treated like polylines. So if we were to right click the clay lens spline set, even though it is a polygon, we only get the option to select along paths. And if I select triangular elements, let me just first remove the selection, and then we'll select along paths, and it's going to select all of the elements along that path. But as you can see, it doesn't actually select all of the elements along that path. So I've puzzled over this. I'm not exactly sure what criteria it's following to either select or not select, one element or the other. But in any case, probably for polygons, it's best to just import them as a property polygon set anyway. Along spline sets and along polylines, it is quite easy to select triangular nodes along that path. So the other question that we had earlier is if I wanted to select all of the nodes along the boundary of the model, but only in a certain location, if we select along paths triangular nodes for the outer bound polygon, we can see it selects all of them. So in this case, if you only wanted to select, let's say, the nodes along the outer edge of the model towards the the southern portion of the model here, you would basically want to create a new polyline specifically for that selection. As with the triangular elements, if we're selecting nodes, we can again click Control or hold Control to select multiple nodes in different locations. Or if I hold Shift, it's going to draw a line the shortest distance between the last clicked node and the new one, and it's going to select all of the nodes along that path. Now, once we've got a selection of nodes that we actually want to export, so for example, if these are pumping wells, then we can select all of them, again, just holding Control here. And what we would then do is we would click Select, Save Selection, and then here we find HydroGeoSphere nchos or elements echos. So you just basically give it a name. We'll call it pumping wells. And then what I would also like to reiterate here is that you should always type in the file extension. So basically include the file extension in the file name itself. If you don't include the file extension, the extension will be there in Windows Explorer, but HydroGeoSphere is going to have trouble actually recognizing it. And we can do the same thing, like, for example, if we had a different property zone, we wanted to have different properties on the interior of this ranch road, then what I would do is just right click, select within polygons, select all those elements. Now the polygon itself is not perfectly aligned with the spline set, so that's something else that you would want to make sure to just kind of correct prior to bringing any of this into AlgoMesh. Obviously, earlier I had made some random changes to this spline set, so it's not surprising that there's going to be some small disconnects. But in any case, I'm not going to worry about that too much. Suffice it to say that we can easily select all of the triangles within a polygon just by right-clicking that polygon set, and then again we can just select, save selection. In this case, it automatically knows that it's elements that we've selected, so we call this, our ranch road property zone. And again, we're going to type in the file name, hit enter. And the last thing that you would want to really export from AlgoMesh, once you've got a finalized mesh, obviously, is the mesh itself. To do that, we're going to click File, Triangular Mesh, and then we're going to scroll down here to Export 2D Mesh to HydroGeoSphere. Now, you are going to see an Export 3D HydroGeoSphere model option here, but just ignore that. So you'll export the 2D mesh to HydroGeoSphere. R5 model mesh. This one you don't have to necessarily specify the file type, but best practice. The one other thing I want to point out here, but I'll leave you to explore this on your own, is the mesh quality metrics, which you access through the mesh menu. So Amanda already talked a lot about these, but it's definitely worth exploring a little bit, running your optimizations at different settings and seeing how it actually impacts the overall quality of the mesh, low versus high. So what I've done here, I think, is I've kind of constrained a lot of these polygons and these constrained edges enough so that low or high optimization settings, we're getting kind of similar results. So I'll leave you to explore that a little bit on your own. Now, outside of AlgoMesh, I do want to spend just a moment exploring how these files actually get used in a HydroGeoSphere model. So in a HydroGeoSphere model, pretty much the entire model input is done through this grok file. And if we scroll down here, we can see that we have a read AlgoMesh 2D grid command, where we just specify the location and the name of the mesh file that was exported from HydroGeoSphere, from AlgoMesh. And that basically defines our 2D mesh for the simulation itself. We then go on and define the 3D aspects of the model by creating new layers and then defining those layer elevations. So we're basically, in this section here, we're taking our two-dimensional mesh and we're adding a vertical dimension to it by specifying layer after layer with elevations just using raster files. And if I just do a quick Control F to find, I can scroll, or I can type in echos, and we can see here that we've got some commands where we basically are first clearing our chosen elements, and then we're choosing elements based on an AlgoMesh or AM file, specify the location of that file, specify the vertical aspect of where the selection is going to actually be applied. So, our clay lens, what's happening here is we're basically saying we want to select all of the elements in this location, and we're doing that between between node sheet 5 and 6. So this would basically select all of these elements within layer, layer 5, I guess. And then we're applying those to a new zone, and then we're reading the properties for those zones. So, if we were not to use an echos file here, we could potentially use a polygon shapefile that would serve kind of the same purpose, delineating the area that we want to select from. Or we would have to start looking at other options like providing a list of node index or element index numbers, or potentially using, coordinates to select elements. It becomes a bit of a not too difficult to do, but there's many different options, and probably the simplest options just for actually manually selecting things and having a bit of a visual aid in terms of where your nodes and elements are selected is to just use eChos and nChos files. If you have AlgoMesh, AlgoMesh can do this for you, do the heavy lifting in terms of your element and node selections. We'll just take another look here at an nChos example. And in this case, we're creating a segment set in our downstream area. So that would be somewhere basically from here all along the edge. Basically, this is the low point in our model domain where we expect water to flow out. And so we're saying basically clear our chosen nodes and then choose the nodes on the top of the model domain, so the top layer, using an AlgoMesh AM file. And we specify the location of our nChos file. We create a set, and then we're using that to basically define a boundary condition. We're doing that again down here, selecting a new set of nodes around the rest of the perimeter of the model and using that to define a critical depth boundary condition as well. And finally, if I scroll down a little bit here, we can see we're using the final nChos from this tutorial to select those pumping node wells. So yeah, that's basically closes the loop in terms of, you create all these things in AlgoMesh. How do you actually use them in HydroGeoSphere? This is all discussed in a lot of detail in later sections. So here in part 3, configuring the grok file. So if anybody here is, interested in ModFlow, you can just stop after after section 2 of the tutorial. But if anybody is really looking to know how to use AlgoMesh specifically in the context of HydroGeoSphere, then part 3 of that tutorial will be quite helpful for you. So that pretty much, I think, wraps up what I wanted to discuss. I mean, there's lots of other little things to explore. We haven't really discussed too much about this active selection section where we can select. Well, first of all, we see some global kind of information about the model mesh, how many nodes there are, how many elements there are, how many elements we currently have selected. And the other thing, actually, it does list here the number of Voronoi cells. We can actually view Voronoi cells. So I mentioned earlier that kind of every triangular mesh has a Voronoi tessellation active in the background. So they're kind of two sides of the same coin. So we can see the Voronoi cells just by activating them in the view menu. We could turn off triangles. And so there you go. Okay, so I'm gonna, I think, leave it at that. The rest of the hour, let's say, for the next 45 minutes or so, I would encourage you to run through these tutorials yourself. And Amanda and I are here to answer any questions. But of course, the trial or the temporary license of AlgoMesh that was provided as part of this training course is valid until April 2nd. So you've got the better part of 2 weeks almost to work through these tutorials as well. So yeah, with that, I will stop sharing my screen for a moment and just check the chat, see if there are any questions. And I do see one question here from Hugh. I'm currently using AlgoMesh 1. Is it recommended to upgrade to AlgoMesh version 2, and how would I go about upgrading? Hugh, I would always recommend upgrading to version, to the latest version of any software, just as a general course of practice. Bugs, as a software developer ourselves, I know that, bugs are always being fixed. New features are always being added. Now, with that being said, I don't believe that there are any major differences in the file format of an AlgoMesh file. I'll share my screen again really quickly here. And what I'm going to do is I'm just going to actually pull up an AH2 output file. So this is the final product. This is the two-dimensional mesh that we're exporting from AlgoMesh. If I just open this up with Notepad, we can see that the file format, this is really the important thing at the end of the day. Now, I'm not 100% sure what the file format looks like for AlgoMesh version 1, but I don't think, I would be surprised if it's very different from, you know, the .ah2 file format. The file format itself is just total number of nodes, and then the XY coordinates of each of these nodes. And if I scroll down, we then have a section that lists the total number of elements, and then the node index numbers, or essentially the, you know, the line that's associated with each one of those nodes to give it the actual coordinates. Amanda, are you aware of any major changes in the file formatting?
No, the AH2 file is the same as far as I'm aware. You can load them in, no changes there. I think the main changes are really just some of the small things like being able to export shape files, having a few more clean geometry tools available within AlgoMesh 2. And I think there were some improvements to the optimization algorithm, so it might run a bit faster. But in either case, you should be able to create a good quality mesh even with version 1. But yeah, you can upgrade. You won't have to pay for a whole new license. It's just a partial fee to upgrade to version 2.
And on the topic of that upgrade, we at Aquanti, we only sell new licenses. And so, you know, if you want to, we can put you in touch with Hydro Algorithmics. You can also just find them very easily by Googling. And actually, I did list in the email, in the reminder email of on Monday, an email address, support@hydroalgorithmics.com. Just send an email to them and they can help you with an upgrade. Now, there's another question from Jonathan. How is the grid quality measured? And that, you know, that basically depends, I think, on the actual grid quality metric. So obviously, every triangular element in the mesh has certain properties, right? We can see that, you know, if we select this mesh is a triangle, so it has 3 angles and it has 3 edge lengths and everything. The mesh quality metrics, you know, there's a couple of different ways that they're actually calculated, but the normalized bisection deviation from centroid, what this is basically measuring is it takes the centroid of the I'm not sure actually in this case whether it's a triangle or whether it's working with the Voronoi cells in the background. This particular mesh quality metrics is more relevant to a ModFlow model, a finite difference model, for example. So what this does is it takes the centroid, I believe, of a Voronoi cell, and then it, you know, the centroid is ideally going to bisect all of the edges of that Voronoi cell at a 90-degree angle. So in this case, it's a normalized bisection deviation from centroid. So if all of your cells were at exactly 1, that would mean that every single centroid bisects every edge of the cell exactly at 90 degrees. So that's the way that that one's calculated. The reciprocal aspect ratio, I believe, is just basically, you know, a measure of the aspect ratio of the triangle itself. How wide is it versus how tall is it? Again, the ideal situation is to have essentially an equilateral triangle. So that, again, would be, you know, the ideal value for all triangles in the entire mesh would be 1. So here, the normalized incircle to circumcircle radius ratio. That's a great question. How is that calculated? I'm not exactly sure. Amanda, do you know?
Yeah, so that one is, well, really exactly what it sounds like. So if you drew the incircle of a triangle as well as the circumcircle of a triangle, and then took the ratio of those, and then this quality distribution normalizes that to a 0 to 1 scale. So again, 1 would be your perfect equilateral triangle, really.
Okay. And then, yeah, we've got the normalized area to side square ratio. So yeah, again, it's normalized from 0 to 1, but it's going to be the, I guess, the area of the triangle to the, if you were to draw a square off of the edge of the triangle. And again, for a perfect equilateral triangle, I guess that would be, they would be exactly the same. Okay, I've got a couple of other, so I guess what happens then is like these mesh quality metrics are measured for every triangle in the entire model domain, and then, you know, they're summarized globally. Okay, we've got another question. If there is a specific area that I want less refined, is there an easy way to reduce triangles in that area other than creating a property polygon set for that area and specifying a smaller mesh cell edge length? Amanda, do you want to field that?
So basically the areas that you want less well refined, there's no other way to do that other than, I suppose, making sure you have a fairly high global max edge length set for your mesh. So naturally anything that is far away from any constrained boundaries would end up with lower mesh resolution.
Yeah, so yeah, it seems just like anything that's outside of a constrained area is just handled through these global settings. So there's really no way to like reduce the triangles in a particular area other than, as you said, using a property polygon. Yeah. So we've got another question. I noticed that the ranch road polylines are not perfectly aligned, especially at the corners. So how do we correct them so that it will represent the actual polylines perfectly? So the way that you would do that, I'm just going to quickly start a new project here. Import that mesh geometry. And then import our ranch road polyline. So if we were to refine the mesh right now, we would see that basically the mesh follows along perfectly with the exact polyline itself. So that includes exactly at these corners here. Now, the reason before that we were seeing, you know, basically like a bit of a skip or a jump from one node to the next is because we had resampled this spline. So if we go to our spline properties, I mean, if you want the mesh to follow along with this exact line perfectly, then, you know, just basically leave it as is. Or what you can do is you can say, instead of doing a sampling per entire spline, what this means is that it's basically, if we said we want to have a vertex starting at, you know, every 10 meters apart, and we apply this to the entire spline, it's going to start off here and it's going to say, okay, 10 meters, add a new vertex. Then another 10 meters, add a new vertex. And then another 10 meters, add a vertex. And sometimes if those new vertices don't land on the existing vertices, then what's going to happen is that you'll have these spots where they're able to skip across one of these existing vertices, and you might end up cutting off the road, like the existing shape a little bit. But if you do the sampling type per segment, then what we'll see here is that it basically takes each existing segment, or, you know, basically the areas between existing vertices, and it's going to ensure that there's at least, you know, if those are more than 10 meters apart, then it's going to add in a new vertex. So what you should do then in this case, where you want the original polyline to still be represented perfectly, but only add in new vertices wherever there's like a large distance in between them, then just make sure that you're sampling per segment. So again, if we change the sampling length here to 1 meter, it's going to add in new vertices along each of these segments, but it's still going to maintain the existing vertices. Okay, now there's another question here. What are the mesh metrics that we need to look at for a HydroGeoSphere model? And I'll give an early answer to that, but Amanda, feel free to jump in and add more detail. But I would say all of the mesh quality metrics should be something that you keep in mind. The first mesh quality metrics that we looked at, the normalized bisection deviation from centroid. This again is something that's, I think, most really more impactful in a finite difference model. But all of these metrics, they kind of go hand in hand a little bit. So basically, and most of these are normalized to 1. So you basically just want to have everything as close to 1 as possible. I wouldn't necessarily even just ignore the normalized bisection rule either. Would you agree with that, Amanda?
Yeah, I don't think you should ignore any of them, but definitely the most important is going to be your aspect ratio, and just your total node count and the range and size of elements. So that's something you could get from the actual eco file or echo file in HGS would give you all of those straight off. But it's really the aspect ratio is probably the most informative when looking at it within AlgoMesh itself. Looking at values really above 0.5 is kind of what you want. But as close as 1 to possible being ideal.
So I'm not seeing any other questions come in. Can you create 3D unstructured grids? That is something that is possible with AlgoMesh, but it's not something that we're familiar with because it's not the workflow that we follow for HydroGeoSphere. But with that being said, there's lots, just like with any other, software platform, there's lots of additional resources that are available. So you can access the AlgoMesh user guide here just by clicking the help menu. And they do have a section here on, I believe that, they've got some sort of short tutorials that go through the entire process of setting up a 3-dimensional mod flow model. So feel free to explore those, but it's not something that we do at Aquanti. Again, for HydroGeoSphere, the workflow that we always recommend is just using AlgoMesh to generate the 2-dimensional triangular mesh, and then we do the rest of the model build directly in in the HydroGeoSphere grok file. Another question is, have we tested the mesh quality versus model performance? And now this is not something I know personally too much about, but mesh quality does have a big impact on the accuracy of your simulation. That's kind of an advanced topic that gets into, it gets into looking at the mathematics behind the flow solution and everything. So it's a bit above my knowledge level. But when you say model performance, there's 2 things that come to mind for me. First of all, the accuracy of the simulation, where mesh quality is very important, but I can't really speak to it very much. The other aspect of model performance is model runtimes. So having a higher quality mesh does actually help with model runtimes in 2 ways. First of all, a higher quality mesh tends to have fewer triangles and nodes overall, as we've kind of demonstrated a little bit. Again, if we were to run an optimization just here based on this simple mesh, run it at a low optimization, 10,000 triangles, run it at a high optimization, and we're going to drop that down by a bit, 9,200. So again, that's going to save a lot of time. So that in terms of model performance, model runtimes, that in itself is a huge benefit. And then the other thing about model performance, again, is accuracy. And accuracy of the simulation also has a bearing on how well the model will run. So having a more accurate model is also going to generally lead to easier simulation convergence. So I don't have any benchmarks or tests or anything that we can kind of discuss here, but general rule of thumb is that a higher quality mesh is going to provide a more accurate flow solution, and it's also going to result in lower runtimes. So in both cases, model performance should increase. Jerome has asked to please just tell me a bit about how HGS is different to ModFlow. That's a great question, and you know, in a nutshell, what I'll say is this: ModFlow only does saturated zone flow for the subsurface, you know, groundwater domain. HydroGeoSphere is a fully integrated hydrologic modeling platform. It performs both saturated and unsaturated three-dimensional flow in the subsurface based on Richard's equation. And it also does two-dimensional overland flow using, I can't remember the exact, the governing equation right now, but it does 2D overland flow. So, you know, in terms of the capabilities of ModFlow compared to HydroGeoSphere, you know, I would say ModFlow can do solute transport, it can do reactive solute transport, it can do density dependent flow, but all of these capabilities are spread across 3 or 4 decades worth of different ModFlow engines. HydroGeoSphere does all of that under a single engine, under a single roof. So, you know, visit our website. Feel free to send me an email. I'd be more than happy to get into the details of exactly what kind of projects you're doing. But you know, I used to work a lot with ModFlow. I was actually the salesperson for visual ModFlow for many years. I can say that HydroGeoSphere does everything pretty much that every generation of ModFlow engines can do, and it does them all together. So it, you know, surface flow, groundwater flow, variably saturated flow, contaminant transport, fracture flow, flow through 1D hydraulic features like channels and tile drains, density dependent flow. HydroGeoSphere supports multiple simulation methods as well. So you can run a finite difference simulation with HydroGeoSphere. You can also run a finite element simulation with HydroGeoSphere, as well as control volume finite difference. So HydroGeoSphere is really, really highly advanced with respect to ModFlow. It, like I said, does everything that ModFlow does and more. Citation for AlgoMesh. Keshav, I'm going to have to follow up with you on that. I don't have it myself, but again, might be just something that I email the developers about, and I'll copy you on that. And Jerome, yes, so ModFlow Surfact and HMS, you're right. Except the thing about ModFlow Surfact is that it, you know, again, it's like it's another third-party engine to ModFlow itself. So you would need ModFlow as well as ModFlow Surfact to do kind of what HydroGeoSphere does. Have we compared AlgoMesh results with the triangle tool mentioned in FlowPy? We haven't, although I'll say that AlgoMesh, it operates on an algorithm, at least for the Delaunay refinement. So the refinement algorithm used in AlgoMesh is pretty much the same algorithm that's used in Triangle. Triangle doesn't, to my knowledge, have all of the optimization, the multi-level optimization capabilities. But at the end of the day, Triangle and the refinement algorithm here in AlgoMesh are performing Delaunay refinement. So the results should be very, very similar. AlgoMesh just has a lot more features, you know, usability features that make make it easier to modify your grids. And it also has that multi-level optimization algorithm. So in that respect, it's I think got a little bit more capabilities than Triangle. Okay, not seeing any questions coming in, but thank you so much, everyone, for bringing those questions up. I again encourage everyone to, if you haven't already got AlgoMesh installed, you can just visit the reminder email that I sent out to everyone on Monday, and you should be able to just basically click on this link here to install. And once AlgoMesh is installed, I was told by the developers that you should be able to just run it immediately. And so I encourage everyone to just spend some time working through either one of those tutorials, and we'll be here waiting for questions. I think now is probably a good time to stop the recording too, so I'll do that.